Hello, good morning. Hello, welcome to the second conference on Applied Geodetic Engineering organized by SIGGMA, AAPG-LUZ Student Chapter, and the Laboratory of Physical and Satellite Geodesy, Dr. Melvin Hoyer. My name is Hermogenes David Suarez, and I have the pleasure of being the host and moderator in this conference. Today, our guest speaker is Professor Dr. Clifford Mugnier. He is presenting a very interesting topic entitled Physical Geodesy of Subsidence in Louisiana. But please let me tell you more about our special guest today. Dr. Clifford Mugnier has had extensive and distinguished career, starting in the United States Air Force, consulting sector, and more recently in the academy, including the University of New Orleans and Louisiana State University. Currently, he is working as instructor in the Department of Civil and Environmental Engineering, Louisiana State University. Dr. Mugnier is the member of many international affiliations. He is serving as editorial member and reviewer of several international reputed journals. Dr. Cliff, with over 300 publications, is ranked in the top 2% of researchers worldwide. He has authored of many research article books, including the very famous series Grid and Datum for the Photogrammetry Engineering and Remote Sensing Journal. In that journal, in that particular publication, he has been covered this grid and datum transformation and historical datum evolution in each country. And that's covered almost all the countries in the South America. He has contributed to the chapter of forensic photogrammetry and on the mathematics and photogrammetry in the Manual of Photogrammetry. His research interests lunar and air topographic mapping, photogrammetry mapping, close-range photogrammetry, geodetic research for a new international boundary treaty between the Republic of Trinidad and Tobago and the Bolivarian Republic of Venezuela. Currently, he's writing a new book. This book coming soon is System of the World Datum and Grids. According to this information, probably next year in January, we can have access to that book. Congratulations, Professor. Finally, and more importantly, Dr. Cliff is the father of 6 natural and 1 adopted and 3 stepchildren, and he has 16 grandchildren and present. For sure, his family is very proud of him. For the audience, the questions or comments can be written through the questions panels and will be answered once the presentation is over. Ladies and gentlemen, please welcome Professor Dr. Cliff Mugnier.
Thank you, sir. Good morning to everyone. Damas y caballeros. I'll be talking on the physical geodesy of subsidence in Louisiana. In English, that means I've been studying the variation in the strength of the Earth's field of gravity within the state of Louisiana, because we are very flat terrain in our state. The highest point, our only mountain, is 356 feet high. And the majority of the southern part of the state is at or below sea level. So flooding is of major concern to the citizens of Louisiana. And because we are in a sedimentary basin, which has been deposited over eons by the Mississippi River, the rate of compaction and subsidence is of enormous interest to the citizenry. When a hurricane approaches the state of Louisiana, one of the primary things of interest to emergency management officials is, when will the highways become flooded? When will people get trapped in their own homes or in their cars and unable to escape to higher elevations? So the ability to predict and to measure variations in elevation due to subsidence is accomplished part by first order differential leveling, which has become too expensive nowadays to contemplate. So the other way to measure this is through GPS observations, which gives us what's called a geometric height or ellipsoid height. And to convert from this geodetic ellipsoid height that we get with the GPS into elevations, we need knowledge of the Earth's gravity field. So that is the reason for the enormous amount of expense and effort we have been producing here at Louisiana State University to determine the variation in ellipsoid heights and elevations due to variations in gravity. Elevation benchmarks do not record ellipsoid heights. Elevation benchmarks are based on the tides, or what is local mean sea level. And with tides in the Gulf of Mexico, they are diurnal. That means one detectable high tide and one low tide. On the east and west coasts, we'll have semi-diurnal tides, which is 2 highs and 2 lows. Actually, that is experienced in the Gulf of Mexico also, but it's so slight that it takes many decades of tide readings to be able to detect the semi-diurnal signal. The effects of the tides are primarily affected by the moon and Chandler motion, discovered in 1880 by an amateur astronomer in the US. The poles wobble. Also affecting the tides is the Great Venus Term, as well as perturbations and nutations of the axes. And all of these different systematic effects occur once in a metonic cycle, which is 18.67 years. So to completely determine local mean sea level, we observe tides at one point at a tide gauge for at least one metonic cycle at one point, which is a tide gauge. Elevations are based on local mean sea level at a tide gauge. So to get elevations transferred to other points or benchmarks, we use spirit leveling, where we set up a rod at a benchmark. We set up the instrument about 60 meters away. We take a backside to that rod and turn it to a 4-point and observe a foresight, and then determine the elevation of the new point. And this continues on while walking physically on the surface of the Earth. So all the benchmarks throughout the world have started at a single benchmark, and then it is traversed by foot or motorized vehicle to set such an instrument as you can see on the screen here at a turning point, and elevations are forwarded that way. Because of this effort, with special Invar steel rods graduated in ½ centimeters, this is where elevation benchmarks have been produced in every continent of the world, even a few small spots in Antarctica, but this is how it's done. This is expensive. Nowadays, to run first order levels, it costs about $1,500 a mile. So looking back in history, Christian Huygens invented the pendulum regulated clock, using the length of the pendulum with a weight to properly regulate the back and forth of the pendulum to maintain regulated correct time. Sir Isaac Newton noticed from the behavior of pendulum clocks that when one was properly regulated at one place and was then later disassembled, transported some distance, few hundred miles north-south, and reassembled, that it would keep time incorrectly. And the difference, according to Newton, he thought was because of variations in the Earth's gravity field, and that the Earth could not possibly be a sphere, but it had to be an oblate ellipsoid, which is squashed at the poles and wider at the middle, kind of like me. Cassini, with a Italian last name, but a Frenchman, had surveyed a series of triangulation arcs in a north-south direction in the province of Brittany, France. And according to his observations, he thought that the Earth was prolonged at the poles and was narrow at the middle. And he proposed a theory that was opposite from Newton. To the consternation of the French, Newton thought, and British geodesists thought that it was a silly idea. So to prove the Englishmen wrong, the French ran two meridian arcs in the north-south direction. The one on the left is along the river Tromsø, which is the border between Finland and Sweden. And on the right, they ran a north-south arc in the country of what is now Ecuador, from a little bit north of the city of Quito to north about 40 kilometers. And this took them several years to accomplish both surveys, and to the consternation of the French, the results of their observation resulted in proving that the Englishman was wrong. The Englishman was correct, and the French Cassini was incorrect. And that was the first published parameters of the ellipsoid of revolution, where we can take a quadrant of the Earth's figure, and this shows that we have developed a coordinate system at the center of the Earth, which is a Cartesian system, and the conversion from latitude, longitude, ellipsoid height into an XYZ coordinate system is a simple geometric transformation. So here's a schematic of the Navstar satellite system, which we nowadays call it GPS, which stands for Global Positioning System. And this is a US Air Force system that is continuous throughout the world. So the difference between elevations and height is that the gravity field is a mathematical equation which models the gravity field, which is called the geoid. The geoid is an imaginary surface where no topography exists and the oceans are only subject to gravity. This is an equipotential surface. Gravity potential is constant, and it's not smooth because of the composition of the Earth and the variation of density in the Earth's crust. And this then results in undulations of the geoid. So the geoid is mathematically expressed as a spherical harmonic, which is polynomials, and it models the relationship between the geoid height and ellipsoid heights. So capital H is elevation, the little green h is ellipsoid height, and the difference between the two is the difference between the surface of the geoid and the ellipsoid, which is capital letter N. And this is just a simple mathematical difference. once we have properly modeled the geoid. So there are two kinds of heights we worry about. One is elevation, which is capital H, which is the blue line from the surface of the Earth to the surface of the geoid. And what we get with GPS elevations or GPS heights or ellipsoid heights is the distance from the surface of the Earth to the surface of the ellipsoid. So it's easy to get with GPS. What's hard to get is capital H, because the unknown is capital N. That's the distance between the ellipsoid and the geoid. And that's the bugaboo that faces us in the field of geodesy and is most important to all surveyors who need elevations. They're not running levels with a differential leveling instrument. They observe heights with GPS receiver, which gives the surveyor little h. And knowing what n is from a geoid model, simple addition and subtraction algebraically gives us then capital H or elevation, and that is of major interest to us. So it's an indirect way of getting what we used to use with leveling instruments. One way that we used to determine geoid height was using theodolite observations. This is a T4 astronomical theodolite. This was a US Air Force instrument that was modified with a digital camera. This is about 25, 30 years ago. A friend of mine, Dr. Herb Stoughton, was the chief geodesist for the Geodetic Survey Squadron in Cheyenne, Wyoming. And they were using this as a way to try and get deflection of the vertical to determine geoid heights. Research in deflection of the vertical since then has progressed significantly. This is a contour map of how the geoid fits the state of Louisiana based on the North American datum of 1927. Now this was determined by astrogeodetic deflection of the vertical, primarily with T4 astronomical theodolites. This chart is obsolete by today's standards, but this is how it was for most of the 20th century. This in front of you right now is a bazillion coefficients in scientific notation. This is what a geoid looks like. Years ago, when I was a young man, this was top secret code word. And geoids have been and still are used for targeting intercontinental ballistic missiles. That's because the missile warhead has to know what the gravity field is as it travels from a launch point to a strike point. Because of the increasing cost of differential surveying for leveling, the Congress directed the National Geodetic Survey to come up with a possible alternative. So in June 1998, the National Geodetic Survey came up with the National Height Modernization Study. That was because the military geoid had been declassified. That list of equations that you saw previous slide with all the coefficients, that was no longer top secret. Since then, they've had the Earth Gravity Model 96, which is 360-degree order, means 360 mathematical coefficients in that polynomial. The geoid 96 was modified by National Geodetic Survey from Earth-wide EGM 96 into just continental United States, 1996. That was at the meter level. And when I did this PowerPoint, this was in 2012, was the current. Now we're into geoid 2022. And new models of geoid continue to be published because of additional observations of gravity. This is the instrument that's used nowadays for geodetic surveying. At LSU, we have one of these. We have an FG5X. So that aluminum vacuum tube you see, ours is see-through. So it's kind of nifty to watch where it continuously drops a prism and picks it up and drops a prism and picks it up over this 1 meter distance. And after a couple of days, everything's added up, divided by the number of drops, and that gives you the absolute gravity or physical acceleration of gravity at a point in a vacuum. And we measure variations in absolute gravity, which is equivalent to measuring 32 feet per second by 12 inches by the conversion for a meter, which gives us 975.36 gals, which is normal gravity. It varies between 976 and 983 because of Newton's observation that the rate of falling of a pendulum varies based on the latitude, because the Earth is squashed at the poles and wide at the center of the Earth. So it's strongest at the poles and decreases as one gets to the equator. And 1 microgal is a millionth of a gal. So when we did some observations of absolute gravity in New Orleans, first time was in March 1989. And you see that number there, where the last digits are 847.7, while in 1994, it's 860.6. So this gradual increase in absolute gravity at just one spot at the University of New Orleans, while I was still there, shows that the surface of New Orleans was getting closer to the surface, to the center of the Earth by this amount. So we have observed absolute gravity in 2002. You see the list of universities and schools in Louisiana. And then in 2006, how we have additional observations at those spots. And now, as of 2022, we have observed many more in the process of developing a baseline of absolute gravity at these points throughout the state. So we have continuously operating reference stations observing GPS at these locations. These are the locations of our GPS permanently receiving stations, where we are now observing absolute gravity periodically at all of these points. And we are seeing variations in the magnitude of the Earth's gravity field at these different points. And what we're looking at is the correlation of changes in absolute gravity versus changes in ellipsoid height. Years ago, back in the middle 80s, I had graduate students measuring relative gravity. Here's one of my base plates that I use for my T4 and BC4 instrument. And he's measuring from a knife blade down to the datum point. And he's observing relative gravity with a Lacoste and Romberg G meter, which measures the intensity of the Earth's gravity field to very reliably to about 1/10 of a milligal, which is about 100 times less precise than an absolute gravity meter. A Lacoste and Romberg gravity meter or a G meter, this was worth about $50,000. An absolute gravity meter is about $440,000. They gave us a $40,000 discount. Here's the new CG5 relative gravity meter in comparison to my old G meter. This is in front of our research center. So the next steps are additional relative gravity observations linking absolute GPS continuously operating reference station sites, as well as to develop a quasi-geoid or gravity model for Louisiana in association with the height modernization program of the National Geodetic Survey. This research is partly funded by LSU and mostly financed by the National Geodetic Survey. So I can answer questions now, or we can go a little bit further if we have any slides left. I think we do. Yes. Okay, this shows long-term observations of GPS ellipsoid heights in the state of Louisiana. This one is on the engineering building here at LSU. That's one LSU. And that is sinking at the constant rate of 4.5 millimeters a year. Here's Boothville Venice High School. That's at 5.8 millimeters a year. This is very close to the coastline. We had a hurricane knock out an antenna for a while, the reason for the gap. And then we resumed observations, and that is still currently in observation. Here's Destrehan High School between Baton Rouge and New Orleans along the Mississippi River. And this is almost 1 millimeter a year subsidence. It's 0.9 millimeters a year. Here's 0.92, which is Grand Isle, U.S. Coast Guard station, where there's also a tide gauge. This is Houma, which is a city between New Orleans and the coast, and that's 4.1 millimeters a year subsidence. This is Lumcon, which is directly on the coast, and this is 7.4 millimeters a year. Here's Thibodaux, which is 6.8 millimeters a year. And these are various spots in South Louisiana, and the variation in subsidence rates is largely due to the type of soil that's present there. In New Orleans, the subsidence due to compaction of the soil is about 8 to 9 millimeters a year, and the muck laid down by Holocene is about 30 to 60 feet deep. Here's Shreveport, 2.8 millimeters a year, very north point in the state. And here's Sicily Island High School along the Mississippi River up north in Louisiana. This is 1.4 millimeters a year. While some areas of the Holocene, the thickness is hundreds of feet thick, 300 to 400 feet thick. And for that reason, the subsidence rates are greater. This shows the GPS network that was analyzed by the National Geodetic Survey with the different major areas of subsidence. So that's pretty much the conclusion of the presentation. We have also been measuring the deflection of the vertical with an instrument we purchased from the University of Latvia. And the US military has developed their own digital zenith camera, vaguely similar to ours in function, at the University of Texas Applied Research Labs. And they have challenged LSU to a Texas-style shootout. So we're going over to Austin in early November, and we're going to compare our zenith camera with that of the University of Texas to compare accuracies as well as speed of observation. So, any questions?
Sure. Thank you. Thank you so much, Professor Mugnier. This was very interesting, your presentation. I really appreciate that. Yes, definitely. We have several questions right now. So feel free to write your questions, send to our question panel. If you wish to do in English or Spanish, is fine. So, Professor, I have one question. It's about in this project. which is basically controlling the ground deformation, the ground vertical deformation in that area. So are you doing something in order to complement this analysis with INSAR technology?
Yes, we have ongoing projects with Jet Propulsion Laboratory, and we're in the process. We do this at 5-year intervals, and we're in the process of proposing further extension of INSAR and NSAR, both with JPL. And we're also trying to co-locate new GPS receivers at abandoned wells throughout the state of Louisiana, so that we can track deep deformation on these wells that have welded steel casings that go down thousands of feet.
Got it. So, Professor, the storms in that area, normally, you know, every 2 or 3 years, some storm hit directly in Louisiana state, especially in the coastal area. So is that storms and the water caused by the storms or flooding in some way increase the subsidence in the area?
We don't think so, no. That's too ephemeral and too short.
Okay. Okay. So to be clear, do you know already what is causing the subsiding effect in that area?
We have various ideas. A lot of them need interpretation by geologists rather than geodesists.
Correct.
But the primary reason is the thickness of the Holocene deposits, those soils that have been laid down since the last ice age in the past 10,000 years. And the recent deposition of the Holocene essentially is an annual process, which is the interleaving of vegetation matter and silt from annual floods. And this interleaving develops a sandwich system that goes through the whole thickness of the Holocene deposit, such that it's highly organic in content, and as well as moisture content. And as the overburden increases, the moisture, the water content of the Holocene is squeezed out. And as a result, we then have resultant compaction. So if you have 20 feet of overlaid Holocene, you're going to have one apparent subsidence rate at the surface versus an area that has 600 feet of Holocene and is compacting. Therefore, you'll notice a surface signal of a much more rapid rate. And the variation of subsidence seems to be primarily affected by the thickness of the Holocene, but it's also, we have significant faulting in central and south Louisiana, and we have slip faults that, as opposed to an earthquake in California, what we have in Louisiana is an ooze. It's slowly oozing down, and the last known earthquake we've had in Louisiana was in 1989 at an area just northeast of New Orleans in Irish Bayou, and the magnitude of the earthquake was such that several dishes were knocked off the wall, which were put up by housewives for decoration, but no damage to buildings.
Okay. So, Professor, a part of the gravity measurement GPS and interferometric SAR or differential interferometric SAR, are you applying a additional to control the subsidence, to measure the subsidence?
I'm sorry, applying what?
I mean, are you using another survey technique for subsidence, a part of the gravity, GPS, and INSAR?
No.
Something extra? Okay. Okay.
No, the only alternative is first order differential leveling, and we don't have the funds available to do that. And we've realized that because of variations in subsidence is so rapid that for the most part, it's a waste of money.
That makes sense. Yeah, that makes sense. Basically, the classical leveling method is too expensive and slow to produce results in this area. So,
about 10 years ago, Professor Roy Daka, he's now passed away. His last PhD student was Dr. Rick Schenkel, who is now employee of NGA in Fredericksburg, Virginia. They did an analysis of all existing first order geodetic leveling in Louisiana, connecting to Pensacola, Florida, which is the closest tide gauge other than Grand Isle. And they discovered remarkable amounts of subsidence that had occurred during the 20th century. And that is a publication which is NOAA NGS Technical Report number 60. And that contains the analysis, the conclusions, as well as appendices which publish all of the first order leveling elevations obtained in Louisiana all the way to Pensacola for the 20th century. So that's available for download for free from the National Geodetic Survey. And it's by the authors Daka, D-O-K-K-A, and Schinkel, S-H-I-N-K-L-E. And just about 100% of that was also Rick Schenkel's PhD dissertation that he worked on under the direction of Professor Daka and myself.
I see. Understand. Professor, someone in the public make this question: why we do have these gaps in the series time here?
Most of them are due to hurricanes that knocked down our antennas, and it took a while for us to reestablish them. Some of them are due to construction. We got a phone call once near the city of Sulphur, Louisiana, that we're about to do some construction work. Come get your antenna. And we went there the following day. And by the time we got there, the only thing left of the building was one part with the antenna sticking up out of the roof. And they had already destroyed the receiver. So various things happen. Primarily, it's due to storms that take out an antenna when some heavy object was flying through the air and takes out the antenna.
I see. More questions from the public. Here is one from Alexander. Probably we already talked about this, but he asked, there is the possibility for this subsiding caused by oil and gas or water extraction. Is that a...
Yes. Yes, it's a known phenomenon now that around each drill rig, you'll develop a cone of depression. but that is very localized and is not likely to extend more than 1 or 2 miles from the rig.
I see.
As well as variations in the thickness of the water table due to dewatering from pumping water and the like. And for that reason, we believe some of the variations in absolute gravity are an expression of hydrostatic pumping of water. We have noticed, so like from our observations of absolute gravity at one of our 2 stations in the Shreveport area, that absolute gravity has actually decreased over the past 20 years, and we suspect that is likely due to pumping down the water table for drinking water in the Shreveport area. So yes, amount of water in the soil will definitely affect absolute gravity observations. And in fact, in areas where it's a significant concern for availability of drinking water from wells, many water districts throughout the world will employ the services of some university to observe absolute gravity to keep track on the amount of water available for pumping.
Okay. Professor, another question from Dario Romero. He asked about the gravitational relationship between Moon, Earth, and this is the question. Variation of gravity are dynamic, and I guess is depend of the closeness of Moon and Sun system altogether. Is there some sort of project that may consider this dynamic variation to consider in the calculation of geoid shape and gravity distribution?
Well, yes, because these are known systematic errors that is modeled for the determination of normal gravity. And when we observe anything with a gravity meter, whether it's relative or absolute, we also observe the time to the closest second of time. And based on that, we then correct for all of these sources of systematic error. We've been doing that for decades. And these are known variations. The moon's orbit about the Earth is the primary cause of variations in gravity, but also the wobble of the Earth's axis, as well as the wobble of the moon's axis, have an effect, as well as the position, like I mentioned in the talk, of where the planet Venus is. And all of these known variations of astronomical phenomena are what contributes to the observation of mean sea level at any point on the Earth's surface of being 1 metonic cycle, or 18.666 years, or 18 years plus 1 January to November. And this is a running average. It varies from year to year. So for the mean sea level for any one point, it's determined at 5 and 10-year epochs. And it's a running average where they will pick up the newest 5 or 10 years and drop the oldest 5 or 10 years. And through this variation from year to year of mean sea level worldwide, this is where they get the figures for the rise of sea elevation and the loss of coastline throughout the world, is through the variance in this determination of metonic cycles.
Got it. Professor, let's say in the operational aspect for those land surveyors doing surveying in that area, I mean, looks like the geoid model for that area is rapidly changing, or it's basically obsolete in some point because the subsidence effect. Is that correct?
Yes, to some extent. For instance, for South Louisiana, we have several hundred benchmarks that are primarily affected because of that. And the National Geodetic Survey is releasing new elevations for South Louisiana, and that adjustment is being released this week.
How often that happens?
As often as National Geodetic Survey wants to pay attention to us, which seems to vary between 5 and 10-year intervals, other than, fortunately, the annual funding of our research here at LSU.
I see, I understand.
All 49 states, their benchmarks are published by the National Geodetic Survey through observations of the National Geodetic Survey, with the exception of Louisiana. And the agency primarily responsible for elevations in Louisiana is LSU, Center for Geoinformatics.
Oh.
We're different from the rest of the nation because of the velocity of changes we experience here.
Right, right. So in Venezuela, we have a similar situation, very close to the Maracaibo Lake. This effect is more related to the oil extraction, but it's also caused by water extraction. So someone asked for where can we find these ground velocities in the vertical component maps. I mean, is that information public, and how can we see those maps in Louisiana?
None exist at present. However, we have full-time researchers working on that sort of thing. The primary researcher nowadays is Professor Ahmed Abdallah,
okay.
Abdalla. And Ahmed's been working on it for the past several years. So essentially, we expect some of this to be published probably in the Journal of Geodesy.
I see. Professor, there is some opportunities for Latin American students to be part of the geodesy group in Louisiana State for master's degrees, PhD degrees.
It's in the College of Engineering, Department of Civil and Environmental Engineering. And if you qualify for admission into the graduate school at LSU in the Department of Civil and Environmental Engineering, you can request Professor Abdallah as your major professor.
Okay, great.
Currently, that's at the master's degree level. And in a few years, we expect that Dr. Abdallah will be also able to direct PhD candidates.
I see. Good.
Officially, I am Emeritus Chief of Geodesy, which means I continue my research. They just don't pay me anymore.
I see. Well, thank you so much. All right, I think there are no more further questions. Well, again, I would like to thank Professor Mugnier for accepting our invitation to this event. And in that sense, I would like to show you and send you this certificate of appreciation from SIGGMA, from the LGFS, is the Laboratory of Geodesy, Physical Geodesy and Satellites in the University of Zulia, and also the AAPG students chapter. So we really, it's a great honor to having you in this session. We have a lot of students connected right now for the Physical Geodesy lecture, and we have more questions, but I will try to resume this for try to complete this session in 1 hour. So again, on behalf of this organization committee, I would like to thank you, everyone who joined today, and we hope you found very valuable this presentation. I also want to remember in January, the new book from Dr. Mugnier is going to be available. Again, the name is Coordinate System of the World, Datums and Grids. This one will be published by CRC Press, Taylor and Francis. And well, for sure, this is going to be a very, very interesting book. So thank you, Dr. Mugnier. And the next webinar is in this second conference will be tomorrow, Saturday at 5 p.m. Venezuelan time. In this opportunity, we'll have Luz Bacaicoa talking about autonomous car and maps for that particular application. And that webinar will be in Spanish from Australia. And please, if you have questions or you need more information, please follow us in our social media platforms. And with that being said, Professor, thank you so much for your time and this opportunity.
My pleasure. Thank you for having me.
Thank you. All right. Thank you so much. See you tomorrow. Bye-bye.